You spin me right round, baby, right round. When we go round the biochem. Okay, so welcome back to my biochemistry video. Today we're going to be going over centrifugation really quick. What exactly is centrifugation? Well, it's technically a purification process that actually allows us to separate proteins and other various molecules by utilizing a centrifugal force. Now, centrifugal force, if you remember from physics, is a force that allows for various molecules to be forced inwards towards a circular motion. Takes advantage of centripetal acceleration, all that good stuff. But we don't really need to understand the physics of it. We just need to understand one equation, and that is the sedimentation coefficient. Now, the sedimentation coefficient is the rate of movement of the molecules under centrifugal force. So some molecules will move faster, other molecules will move slower, depending on the value of their sedimentation coefficient. Now, this is the equation of the sedimentation coefficient right here, and this is the sedimentation coefficient. S is sedimentation coefficient. The thing to know here is the smaller the sedimentation coefficient, the slower the molecule or protein in question is moving in the centrifugation. This is mass. This would be velocity, this would be density, and this would be the frictional molecular shape, which don't really worry about these, just understand how this equation could work. And really the concept you need to get from this is that if S is smaller, it's going to be moving slower, and if S is larger, it's going to be moving faster under a centrifugal force. So to recap, that sedimentation coefficient is the movement of molecules at various speeds under a centrifugal force. So basically taking advantage of this equation to understand what molecules will move at what speed under a centrifugal force. Now, once again, this relies on three things: mass, density, and shape. As you increase the mass, of course, your sedimentation coefficient is going to increase, meaning it is going to be moving faster under that centrifugal force. As you decrease the mass of the molecule or protein in question, you are going to decrease your sedimentation coefficient, meaning it's going to be moving slower. Now, if we look at density, once again, as density increases, that would also mean that your sedimentation coefficient is going to increase, because this is, once again, right here, this portion, the numerator. So the numerator is going to be getting larger, meaning that if density increases, your sedimentation coefficient is going to increase, increasing our speed of the molecule or protein in question. Now, then the one thing that actually can decrease the sedimentation coefficient and increase also, I guess you could say, is the shape of the molecule. So if it has more surface area, it's actually going to be moving much slower in the solution it's present in when it's under that centrifugal force. So for example, say you have a test tube and you have something that is awkwardly shaped and you have something that is smooth. The smoother object's going to be moving faster under centrifugal force because its frictional molecular shape would actually be lower. Now, if it's this awkward shape, it's going to actually have a larger frictional molecular shape, which is going to increase that friction and cause it to be slower. So once again, to reiterate that, if you have an awkward shape, your sedimentation coefficient is going to go down. And if you have a smoother shape, less friction, less surface area, your sedimentation coefficient is going to go up, meaning that it is going to be traveling faster. And yeah, that's basically how you utilize this formula. Just kind of take a look at it, and the three things you really need to know is the mass, the density, and the shape, and how that all correlates to this formula right here. But I basically just explained everything you need to know with that. Now then, moving on. As things move faster under a centrifugation, they're going to appear at the bottom of the tube. Once again, because that's going to be where your thick boys are. The larger molecules are going to appear at the bottom of the tube under a centrifugal force. Your denser proteins, of course, are also going to appear at the bottom of the tube after undergoing a centrifugal force. Your smaller molecules or smaller proteins are going to appear at the top. So, if you recall from my previous video, we went over how to form a homogenate, and the homogenate was basically how you break up a cell in order to obtain the cytosol, which is a soluble protein that can then be used under purification processes. And if you recall, the cytosol was here in that pellet, which was the dense cellular portions of the cell, such as the mitochondrial fragments, microsomal fragments, nuclear fragments, were here at the bottom. And once again, if you recall, we did use a centrifugal force in order to separate those proteins from the fractions of those various cellular components. And once again, this makes sense because cytosol, which is very liquid-like as the soluble proteins, was at the top, and then that thick, dense, awkwardly shaped cell components such as the mitochondrial fragments, microsomal fragments, and the nuclear fragments were at the bottom because those are way more dense, way more awkwardly shaped. So this all makes sense. It's all starting to tie together. But let's just make sure you guys understand the concepts before I end this video. So what protein would have a smaller S value? You have one protein with a molecular weight of 81 and one protein with a molecular weight of 21. Well, the one that would have a smaller S value, of course, would be protein 2. And if you go back to the equation, you would understand that, because if you plug that in, the mass is smaller. We can ignore this stuff, and overall we can just know that since the mass is smaller, the sedimentation coefficient would be smaller than protein 1, because protein 1, of course, has a larger mass. So what can we say about this? If we know that protein 1 has a larger S value, and protein 2 has a smaller S value, what one would be moving faster under centrifugal force? And also, just for fun, let's see where would it end up in a centrifuge tube, or a test tube that is under centrifugal force. I'll give you a second to answer that. If you said this molecule, protein 1, is moving faster, you would be 100% correct, because protein 1 has the larger S value due to that larger molecular weight. Protein 2 would be moving slower, so it would have the lower S value due to that smaller molecular weight. Okay? So, I hope you understand that concept. Now then, just for fun, once again, where would it be located in the tube after we were done applying centrifugal force? Well, this molecular weight of 81, these large, thick boys, would be towards the bottom here. And these less thick boys, well, these smaller boys, the 21 molecular weight proteins, would be more towards the top. I guess another way you could think of this is the larger the sedimentation coefficient, the more likely you are to be at the bottom of the centrifugal force, or the centrifugation tube, and the smaller your S coefficient is, the more likely you are to be at the top of the centrifugation tube. And that's basically the concept to get out from that. But yeah, quick video. Hope this made sense to you guys. If not, leave a comment. Yeah, stay frosty.